The Forward Secrecy Problem. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are taking a comprehensive deep dive into a critical feature of modern cryptography: perfect forward secrecy. We will discover the hidden danger of using long-term keys, analyze the flawed protocols of the past, and learn how the elegant solution, Ephemeral Diffie-Hellman, protects our past conversations from future attacks. This is the story of how we learned not just to secure our present, but also to protect our past. The core question. Let's start with a simple but powerful question that gets to the heart of what we're talking about today. Can a secret key that is stolen tomorrow be used to break the encryption of a message you sent yesterday? For a long time, the answer was unfortunately yes. This presentation is about why that was the case, and the brilliant solution the cryptographic community developed to change the answer to a definitive no. Defining perfect forward secrecy. The solution to that problem is a property called perfect forward secrecy, or PFSA protocol that has PFS ensures that if a long-term key is compromised, it does not compromise any past session keys. Think of it like this. Every secure conversation you have takes place in a unique, soundproof room. At the end of the conversation, the room, its key, and everything inside it are instantly vaporized. Even if an attacker later steals the master key to the building, they cannot get into the room you used yesterday, because it no longer exists. Each session is a cryptographically isolated event. The threat model. Record now, decrypt later. The importance of forward secrecy became a major public concern following the Snowden revelations in 2013. These disclosures revealed that intelligence agencies were engaged in mass surveillance, often recording and storing vast amounts of encrypted internet traffic. The strategy was clear. Record now, decrypt later. They would hold onto this data for years, hoping that a future breakthrough, whether it was a clever mathematical discovery, a stolen key, or a court order, would allow them to retroactively decrypt this treasure trove of past communications. This threat made forward secrecy a top priority for protocol designers. The foundation. Key exchange. Before we can understand the flaw, we have to remember the goal of a key exchange protocol. Its job is to allow two parties, like your browser and a web server, to agree on a shared secret key over an insecure network. This shared secret is then used to generate symmetric keys, for example, for ESGCM or Cha-Cha-Poly, that will encrypt the actual data of your session. The key exchange is the foundation upon which the entire secure session is built. If that foundation is flawed, the whole structure is at risk. The root of the problem. Static keys. The fundamental problem comes from using static keys. A static key is a long-term secret that is reused for many different sessions. Think of it like the master key to a building. It can open every single door. In cryptography, this often meant a server would use the same private key, stored on its hard drive for months or years, as a starting point for every single secure connection it established. While this is computationally efficient, it creates a single, catastrophic point of failure that violates the principle of session independence. The Static RSA Handshake. The most classic example of a handshake with no forward secrecy was the old Static RSA Key Exchange used in early versions of TLS. Here's how it worked. The client would generate a secret number, called the pre-master secret, and then encrypt it using the server's long-term public RSA key from its certificate. The client would then send this encrypted value to the server. The server would use its long-term private RSA key to decrypt it. Now they both have the pre-master secret, which they use to generate the session keys. The entire security of the session depends on that one, single, static server private key. The static RSA attack path. The vulnerability here is stark. An attacker records the encrypted pre-master secret during the handshake. At the time, it is just gibberish. However, if the attacker ever manages to steal the server's long-term private RSA key. Even years later, they can go back to their recording, decrypt the pre-master secret, and then derive the exact same session keys that were used. They can now decrypt the entire recorded conversation. Every past session encrypted this way is retroactively compromised. This method is now considered completely insecure and has been removed from modern protocols. Legacy flaw. Static Diffie-Hellman. Now, let's apply this to Diffie-Hellman. The problem is very similar. A server could be configured to use a static, long-term Diffie-Hellman private key, B. Its corresponding public key, B, would be embedded in its certificate. When Alice connects, she generates a temporary key A and public key A. They perform the exchange, and the shared secret is derived from A and B. When Carol connects, she does the same, and the shared secret is derived from her key and the same public key B. The server's key, B, is the common factor in every single key exchange. The static DH attack path. This illustrates the catastrophic payoff for the attacker. Months after recording the traffic, Eve successfully hacks the server and steals its long-term static private key, B. Now she can go back to her archives. She takes her recording of Alice's public key, A1, and combines it with the stolen private key B. She performs the same calculation the server did months ago. S1 equals B times A1. She now has the session key for Alice's entire conversation and can decrypt it. She can repeat this process for Carol, David, and everyone else whose handshake she recorded. The entire history of the server's communication is now compromised. The common vulnerability. Let's summarize the core problem of all static key exchanges. A single long-term private key is used to generate or unlock the session keys for many different sessions. This creates a cryptographic link, a single point of failure, connecting all of them. An attacker who records the public traffic and later compromises that single long-term key can break the security of every single one of those past sessions. This is the exact opposite of what we want. We need each session to be an independent, cryptographic island. The ephemeral solution. The solution to this problem is both simple and elegant. Use a key once, and then discard it. This is called Ephemeral Diffie-Hellman, or DHE when using elliptic curves. It is ECDHE. The word ephemeral means temporary or short-lived. In an ephemeral key exchange, there is no long-term key used for the exchange. Instead, both the client and the server generate a brand new, temporary key pair for every single session. Once the session is over, these temporary keys are securely discarded and never used again. Meet ECDHE, the modern standard. The modern implementation of this idea is Ephemeral Elliptic Curve Diffie-Hellman, or ECDHE. It follows the exact same Diffie-Hellman recipe, but with two crucial changes. First, it uses the efficient mathematics of elliptic curves. And second, the keys used for the exchange are generated on the fly for each session and then discarded. This combination provides both high performance and perfect forward secrecy, making it the gold standard for modern key exchanges. The ECDHE handshake. Step 1. The client hello. Let's walk through the modern handshake step by step. It begins when your browser, the client, wants to connect to a server. First, the client generates a brand new, temporary ECC key pair just for this session. We'll call the private key a temp and the public key a temp. The client then sends a client hello message to the server, which includes its public key a temp and a list of the cipher suites it supports. The ECDHE handshake. Step 2. Server hello. The server receives the client hello. It sees the client's temporary public key, a temp. Now, the server does the same thing. It generates its own brand new, temporary ECC key pair just for this one session. We will call its private key, btemp, and its public key, btemp. The server then sends a server hello message back to the client, which contains its ephemeral public key, btemp. Step 3. The authentication problem. But this creates a new problem. The client just received a temporary public key, btemp, from someone on the internet. How does the client know that this key actually came from the real server and not from a man-in-the-middle attacker who just made it up? The ephemeral key itself carries no identity. If we just proceed from here, we are vulnerable to an impersonation attack. We need to tie this temporary key to the server's long-term, trusted identity. Step 4. The signature, the key's new job. This is where the server's long-term key comes into play. The server's static key, the one in its certificate, changes its job. It is no longer used for secrecy. Its only job now is to provide identity. The server takes all the important handshake information, including the client's ephemeral key and its own ephemeral key, and creates a digital signature over it. This signature is created using the server's long-term, static private key. It's like a notary stamping a document, certifying that the temporary key is authentic. Client verification. The server now sends its ephemeral public key, btemp, its certificate, and the digital signature to the client. The client performs a critical verification step. It uses the server's long-term public key, which it gets from the certificate and trusts because of the CA system, to check the digital signature. If the signature is valid, the client now has mathematical proof that the temporary key btemp is authentic and belongs to the real server. The man-in-the-middle attack is foiled. The shared secret. Only after the server's ephemeral key has been authenticated does the client proceed to the final step. The client takes its temporary private key, a temp, and the server's authenticated temporary public key, btemp, and computes the shared secret S equals a temp times btemp. The server does the same calculation with its private key and the client's public key. They both arrive at the same shared secret and can now begin encrypting the application data. The handshake is complete. Step 7. The cleanup. This is the final, crucial step that guarantees forward secrecy. As soon as the shared secret has been calculated and the session keys have been derived from it, both the client and the server securely wipe their temporary private keys, a temp and btemp, from memory. These keys existed for only a fraction of a second and will never be used again. They are truly ephemeral. This act of cryptographic hygiene is what breaks the link between sessions and protects the past. A complete visual handshake. This sequence diagram shows the entire flow we just discussed. The client sends its ephemeral public key. The server responds with its own ephemeral public key, its certificate for identity, and a signature to prove ownership of the ephemeral key. The client verifies the signature, and only then do both sides compute the shared secret and proceed to the encrypted session. This multi-step dance ensures both secrecy and authenticity. The payoff. Security after a compromise. Now, let's revisit our attack scenario. Eve has been recording traffic for months, and today, she finally hacks the server and steals its long-term private key. What can she do? She can use it to impersonate the server in future handshakes. But what about all the past traffic she recorded? It is completely useless to her. The shared secret for Alice's past session, S1, was derived from the ephemeral private key B_temp1, which was deleted from the server's memory months ago. The stolen long-term key provides absolutely no information about those old, discarded ephemeral keys. The past remains secure. Forward secrecy versus backward secrecy. Forward secrecy protects past sessions from a future compromise of a long-term key. There is a related concept sometimes called backward secrecy or future secrecy. This ensures that a compromise of a single session key does not compromise the long-term master key. Because the session keys in ECDHE are derived from the ephemeral keys and not the other way around, this property is also maintained. The security is one way. Compromising a leaf on the tree doesn't compromise the root. What about session resumption? A smart question might be, doesn't doing this full handshake for every single connection slow things down? Yes, it does. That is why protocols like TLS have a feature called session resumption. In TLS 1.3, this works by having the server give the client a special session ticket after the first handshake. This ticket is encrypted with a key known only to the server. On a subsequent connection, the client can present this ticket to resume the session, skipping the full handshake. Crucially, the keys used to encrypt these tickets are rotated frequently and are separate from the long-term key, so forward secrecy is maintained. Performance overhead. Is it worth it? So, is all this extra cryptographic work, generating a new key pair and creating a digital signature for every single session, a performance bottleneck? While it is technically more computationally expensive than a static key exchange, the answer is that it is absolutely worth it. The math of ECC is incredibly fast on modern hardware. The cost of generating a new key pair and a signature is measured in microseconds. It is a negligible price to pay for the massive security guarantee of perfect forward secrecy. Static versus ephemeral. The final showdown. Let's summarize the key differences. In a static exchange, the server uses one long-term private key for both identity and key exchange. This is efficient but lacks forward secrecy. A single key compromise decrypts all past and future traffic. In an ephemeral exchange, the server uses a long-term key for identity, signing, and a unique, temporary key for each session's key exchange. This is slightly more computationally expensive, but it provides perfect forward secrecy. A compromise of the long-term key only affects future sessions, not past ones. Given the massive security benefit, ephemeral modes are the standard for all modern protocols. The modern standard, TLS 1.3 and beyond. Because of its powerful security guarantees, Ephemeral Diffie-Hellman is no longer an optional extra. It is the mandatory standard for modern secure communication. Protocols like TLS 1.3, the latest version of the protocol that secures the web, have completely removed support for static key exchanges. The only key exchange modes allowed are ephemeral, ensuring that all connections automatically have perfect forward secrecy built in from the start. This is a huge step forward for privacy and security on the Internet. Why forward secrecy is the gold standard. To conclude, perfect forward secrecy is the gold standard for secure communications because it adheres to the principle of cryptographic hygiene. It treats session keys as disposable secrets, ensuring that each conversation is an independent cryptographic event. It contains the blast radius of a key compromise, protecting the integrity of past communications. In a world where long-term data recording is a reality, this is not just a feature. It is a fundamental requirement for true privacy. Conclusion. We've seen how the simple approach of using static keys leads to a catastrophic long-term vulnerability. The solution, Ephemeral Diffie-Hellman, ECDHE, elegantly solves this by separating the key for identity from the keys for secrecy. By using temporary, disposable keys for each session's key exchange, we gain the crucial guarantee of perfect forward secrecy. This ensures that even if a server's master key is one day stolen, the secrets of our past conversations remain safe. Final thoughts. The concept of perfect forward secrecy represents a mature understanding of cryptographic threats. It's not enough to protect a conversation today. We must also ensure it cannot be decrypted tomorrow. By embracing the principle that session keys should be ephemeral, we build systems that are resilient to future failures. ECDHE is a testament to the continuous evolution of cryptography in the ongoing effort to protect our privacy. Thank you for your attendance. Please consider subscribing to the channel.